So are we, do you think that systems as they grow, math being the most fundamental system of pattern formation, let's say, and then get into physics and biology, do you think that patterns that you see in math repeat through the larger, I don't want to call them sciences, but as systems conglomerate and form matter and then above, do you think that those patterns repeat or brand new patterns are formed, and so we need eventually brand new math to describe, I don't know, weather patterns or something?
I think, sorry, I keep looking as if my inspiration is over here. I think that what we really are saying, if we investigate, if let's say in some scientific endeavor, we investigate some new phenomenon, we may very quickly see mathematical ideas and models that we already have that adequately describe those things. That's not going to be that surprising if there's some fundamental mechanism behind it that we already understand. So if we go to some different planet and we see the way that geology works on that planet, it may not shock us to find that some of the existing mathematical models for geology that we have will describe what goes on there, because there's some fundamental mechanic that works, or mechanism that at work. But if there's a new mechanism that we don't understand, that we're trying to explore, it's not clear what the mathematical underpinnings of that will be. And so sometimes there are examples where mathematics that we have in other realms perfectly fits and describes what that new thing is. Of course, the classic example that we have now is quantum mechanics, right? People trying to understand what goes on inside the atom, which I don't know very much about, but I know that this story is accurate. They turn to mathematical structures, algebraic structures, that people in mathematics developed entirely on their own without even thinking about physics. And what they found is that even though physically we have difficulty describing, are these waves, are these particles, like it's hard to account for all the things that are going on inside the atom, some of these mathematical structures that were invented entirely for abstract reasons by other people perfectly describe those things. That's amazing. There's some underlying reason why those mathematical ideas developed way over here by all these other people perfectly describe this thing in physics, but we don't know why that is really yet. All we know is that it does in a lot of ways, and we say, oh, that's fortuitous. So I don't know why that is, but the answer for why that is maybe we'll find in 100 years, or maybe we'll find in 3 years. So I think that kind of thing will happen, and that's an amazing and wonderful thing. And of course, there are plenty of situations where it doesn't happen, where we're trying to model a thing, we have no idea how to do it mathematically, and we need to develop new math to do it, and we just don't know what that is yet.
What do you hope happens in the next 10 years in math education?
Oh, okay. So in the next 10 years in math education, I don't know what I should say, pie in the sky or realistic.
For 20 years.
There are a couple big problems that we have in math education right now. And some of those problems are structural problems in education in general. So we're not, and I don't want to talk about those because I don't understand that world that well. I'm not an educational administrator. But, teachers who don't have the support and the training in order to do what they need to do. I mean, some of that is there needs to be more resources available for them and so on. So I'd like to see some of that happen. But let me say just for math education research, as researchers, what do we need to do in the next 10 years? We need to develop careful learning trajectories for these different areas of math that people are studying. I think what I would say is our primary task. So we need to come up with good problems for students and chart out the ideas that they develop through these problems and come up with new problems that move the students incrementally to these key understandings that we want them to have. Right now, mathematical ideas or mathematics content in the classroom is organized according to topic. Today, we are going to learn the law of exponents. And then that is delivered to the students, but they themselves they don't learn that through their activity, through the tasks that they're given. They don't create the need for that new general idea themselves, and then have that generalization come in order to solve that problem. They're given the generalization first, and then they're asked to practice it. Okay, so the big task for math education is how do we give them tasks that necessitate the development of that idea, rather than just giving them the idea and letting them practice it. So that right now we're working on that in certain areas, and some are well developed and some are very poorly developed. We don't understand the sequence of tasks and the sequence of understandings that come from them very well at all. So I think in the next 10 years, to have that kind of charted out better is one of the main goals for math education research.
Are math researchers, other math researchers, on board with you, or are you kind of a maverick in this?
No, I'm not a maverick. I would say there are plenty of other areas of research in math education that are extremely interesting and exciting and fruitful to pursue. This is just one. I actually came back from a conference a couple days ago where the keynote speaker talked about this very thing. And I don't think that he's representing what the entire math education research community says. I think he's saying there needs to be a crew of people that are working on this kind of thing. Okay. And it's the thing that I'm most excited about in math education research, but there's a lot of other things that matter too. So.
But my question is, you haven't encountered a lot of resistance to this idea, have you?
No, I mean, I think that there's some resistance. I don't want to be too political here. I think that there's some resistance, just because I don't know very much about that the political side. There's some resistance in some of the schools if people think that that actually isn't teaching. Okay, if they think that what teaching is telling the students the general idea and then letting them practice it. Some people, because they didn't have a chance to learn through their own activity, and by tackling difficult problems and tasks and necessitating those mathematical ideas themselves, if they didn't have to learn that way or never had an opportunity to learn that way, they may not actually understand why that is real deep learning. So there is some resistance perhaps on that way, but most of the time people aren't stopping math education researchers from doing what they're doing. They may just simply dismiss the results and say, we'll just do it our old way and it's going to be fine.
Well, thank you, Dr. Ely, for coming to see me. It's been really a pleasure to talk to you today.
Oh, thank you very much. I'm glad to be here. Awesome.